Hi everyone, and today what we're going to walk through, as you can see from the title, we're going to get into some trigonometric applications. So to start off today, just with a little bit of a review to make sure that we're good with what we need walking in, what you see on your page is a quick picture of a sinusoidal function. So what I would like you to do is to create an equation, sine and cos, that's going to resemble that. So pause the video now, give it a shot. Okay, we should be back. We should notice that the height of that graph is 6 units, and therefore we had a vertical stretch by a factor of 3. We should also notice that then if I went 3 down from the top or 3 up from the bottom, that's going to give me a middle value or equation of axis of 1. Then when we take a look at the period, we'll notice that to complete one full cycle is going to require pi units. And so my normal sine or cosine curve take 2 pi. This one only takes 1 pi, and therefore there's been a horizontal stretch by a factor of 1/2. So my k value is 2. And again, just like last time, you can always use your period equals 2 pi over k, divide out your pi, multiply out your k to go through and solve. Now that we have all that information, okay, let's build the equation. Well, because when I look at that graph, I notice that that graph starts at the top and falls right now, that matches my normal cos curve. So I would hope that everyone would have built a cos graph first, because that one requires no phase shift. Now, I also gave you the instruction, though, to also find a sine curve. So this one's going to require a little more work in just that it's going to need a phase shift. So I know that my amplitude's the same. I'm going to have my horizontal stretch. The only thing now that I need to plug in is what my shift is. This would be a case where, again, it's my personal preference, that when I go to the middle of the graph, that's my first value, first positive value where I'm at the middle of my graph. And so that graph is in the middle and falling. That means that it would require a negative sine curve, and then I could shift it to the right 1/4 of that pi, and so a pi by 4. That would have been the graph that I would have created. However, there are so many more. I think it would have been totally expected if I would have had a bunch of people who then said, but to match on my graph, and I'm just going to erase everything that I've put up here, that this would be the first point where I'm in the middle of my graph and rising like a normal sine curve. And so I would have had to shift it over 3/4 of pi to build that equation. I think those would all be pretty representative equations. However, I do think, though, that I may have had some people who would have liked to have shifted the graph left, especially since they can see the graph left of the y-axis, because there's a position where the graph starts in the middle and rises. And so perhaps we used a positive sine curve, but chose to shift it left pi by 4 instead. Those would have been the common equations I would have expected to see. Hopefully yours fell into those. Okay, let's jump into some application questions now. And so as you take a look at problem 2, I'd like you to pause the video and give question 2 and then part A a read. Okay, pause it now. Okay, and we're back. So you take a look at that problem. We've got a windmill. It's got its center at a certain height. It has blades of a certain length. In a steady wind, this point P at the tip of a blade makes a rotation. If the rotation begins at the highest point, determine a function. So the actual instruction in the problem is going to be determine a function. And what that means is I need the equation of that function. Okay, so if I was to go through and build this function, what it says is I have a windmill, and I'm just going to draw this big circle. This is really the center of the windmill, but I have these blades that are coming out. And as these blades come out on the windmill and then rotate, that is going to create my circle. The faster it rotates, I'll actually get an appearance of a circle. So the problem says that I have point P at the top. And what I want to make sure we're good on is that we don't think that that is the picture of the graph. That if we were to go through and now graph what happens to the height of P as time passes, we should be good to construct an actual graph of the function of height versus time. So what I'm going to do is I'm going to come over here and I'm going to produce a quick set of axes. I'm just going to get rid of that equation up in the top because we now know that's what we need to do. My axes are going to be height versus time. And now what I'm going to do is I'm going to draw the picture of what happens as P begins to rotate. So the first thing that's going to happen, point P is going to start at its maximum height. Now, what happens to point P? Well, as P starts to rotate, notice that in this first part of the rotation, we have all of this horizontal distance that has to happen. So for instance, it takes this long for us to get there, and our point P only dropped a little. We then get to a certain point where our point P drops a lot. In this small little distance, notice point P is going to drop a lot to get down to that new position. Now, that might be a little confusing right now, but you're going to see that show up on the graph. That at the very beginning of my curve, I'm not dropping very quickly. So my height is decreasing only a little bit as time goes on. But then what happens is I get to the side of my curve and all of a sudden I decrease a lot. On my graph, that would be the purple followed by the red segment. So we can tell then that point P is not going to be linear in its height change over time. And so then I get towards the bottom and then I wrap back up towards the top, and that would be one complete rotation of point P. Okay, I'm going to get rid of my really, really crude windmill over on the side. And what I'd like you to do right now is, on that graph, I'd like you to label the maximum value, the minimum value, and the period of your graph. So pause the video now, go ahead and do it. Okay, we're back. So, a couple things when we take a look at the problem. I'm hoping that we matched up with an 8 meters. I'm hoping that we matched up with a 4 meters. And I'm hoping that we matched up with our period of 12 seconds. Now, I would be totally fine if you actually labeled this point and you said, like, I have a minimum value of 4 and I have a maximum, but that is totally fine as well. However, you don't need any of that. That if we labeled those 3 things on our graph, you actually have as much as what you need. Now, how do we get to those? Well, the first thing, we notice that the center of the wheel is at 6. So some people may have chosen, and they may like to label the middle of their graph as well. You'll then see the blade is 2 meters in length. So therefore, from the center of the wheel to the very top, to where point P is, could be 2 meters above and 2 meters below. So As I said, there's all the important information. I'm going to leave the gold on right now, that 6 meters, just so we can see it in the end. However, you would never need to write it. Okay, what you'll notice is what you have in that crude sketch is you have the sketch of a sine or a cos curve. And what we spent last time doing in the beginning of today is being able to create the equation when given the graph. So, if you have the ability to go through and build the equation for this crude sketch, then once you have the equation of the function, you can do almost anything. So, what I'd like you to do now is pause the video, and I want you to build the equation for that graph. Go to it. Okay, we should be back. So, if I was to just label out properties, we should be able to see that we would have an amplitude of 2. We can see that we have the middle of our graph at 6. That's why some people like to have the gold put on their diagram, although it would never be needed. We can also tell that we have a period of 12 seconds. Now, I want to maybe go through something with us just to make sure that we really understand what we're dealing with in this context. That I want to come back to this statement about period. But we're going to go off and we're going to do some stuff with it first. So, because the period is 12 seconds, then I know my period is always equal to 2 pi over k. I can multiply out my k value and then divide out the 12 and reduce. And I see that my k should be pi by 6. Okay, that means then that I can go through now and I can build the equation of the function. Just notice what your variables are. They're not going to be y and x. We're going to deal with h and t. So the height of point P on that graph is going to equal an amplitude of 2. I would hope everyone would have chosen cos for this graph because that's the way a cos curve normally starts. It'll avoid a phase shift. I have my stretch k in there. There's my independent variable t. Move up to the middle of my graph, and that blue equation will represent that function. Okay, there we go. Nice. Okay, let's take a look at problem B. What is the height of P at 5 seconds? So we're asking, what is the height of P at 5 seconds? Now, I would hope that we would all be good that once we had the equation of the function, you could simply sub in t equals 5. But I am going to have some people that have a little bit of an issue for a second. And here's why. That when we take this function and we replace the t with 5, some people are going to have a little bit of a hiccup. That is, when they simplify this, and they now have to calculate cos of 5 pi by 6, in that value of 5, they subbed in a time. But when you calculate cos 5 pi by 6, 5 pi by 6 has to be an angle. So how did time change into angles? And more specifically, how did time that's being measured in seconds somehow become an angle which is measured in radians? I want to come back to the part that I said I wanted to address earlier, this whole idea of us having periods that aren't in angle measurements. And I need to hop back to jump into science mode for a second. When you guys go through and you guys use equations in math, we put pressure on you to not put your units in your formula. It's bad form. And then as soon as you walk into a science class, your science teacher tells you to put your units in everything. I want to jump back into that unit aspect for 1 second so we can understand what we see in B. That relationship of period equals 2 pi over k is a way to come up with a stretch factor, but it's also a way to come up with unit conversion, that we can have a conversion factor that will allow us to change units. So I'm going to go back and I'm going to just put in my units in this problem. So my period is being measured in seconds. My angles, 2 pi, are being measured in radians. And so when I multiply out that k, and then I divide out my seconds, what I'm actually getting in this case is a value, in this case, pi by 6, that was radians per second. My k value actually becomes a way for me to go through and convert units. Okay, how do you see that? Well, that's going to require me to come back and just get rid of all this blue. And now I'm going to fix up that red in a moment. In red. Put my units back in my equation. So what we end up seeing then is that when I have my pi by 6, I'm just going to use R for radians. That would be my radians per second. That when I actually sub in that 5, I'm subbing in 5 seconds. And so when I do the calculation of pi by 6 times 5, my seconds divide out. And that's what ensures that 5 pi by 6 is actually in radians. And so now when I go to calculate the cos of that, I have the ability to do it. So when we solve for our k value, we're actually coming up with a conversion factor as well. So for anybody who was hung up on, wait a second, so I can take the cos of a time, you're not calculating the cos of a time. You're still calculating the cos of an angle. Okay, we get to that point, and because the problem is an application question, you can round some stuff off. I just want you to be prepared for, though, what if I asked you what is the exact height of point P? Now we lose the ability to round. So let's make sure that we're good with how to deal with it without rounding. You guys are all fine to deal with cos of pi by 6. Your cos of 5 pi by 6 is going to end up being pi by 6 short. That pi by 6 means that we have this as a rotation angle, and therefore your cos 5 pi by 6 is adjacent over hypotenuse. And so if you had to come up with an exact value, you would tell me that it was 6 minus root 3 meters. Now, we don't talk about it that way, so you would convert that into a decimal and approximate it to about 4.27. There we go. Okay, we're good to be able to use the equation. I think the next question then has to be, why are you wasting our time with it? So when you take a look at part C, you'll notice what is the height of point P at 40 seconds. Everybody should be fine to do the exact same thing in red and sub in t equals 40. I just want to stop for a second. Because for us to be able to go through and use t equals 40, first off, I'd want us to be able to at least estimate what that answer should be. But also, I want us to be efficient with it. That when we sub in t equals 40, you're now going to get something that looks like this. Well, pi by 6 times 40 is going to be 40 pi by 6. That, of course, reduces. So you would be trying to now figure out a rotation angle for 20 pi by 3. So now we're going, well, if that's pi by 3s, then I have a full rotation. There's a 6 pi by 3, and then another full, there's a 12 pi by, then another full rotation there. And so we get to this point then where we have to start taking out our full rotations and instead then going, okay, so now that I've completed 3 full rotations, I have 2 pi by 3 left over. And so now I rotate the 2 pi by 3 and I have my means to solve. That is where most students make their mistake, is having to deal with a bunch of rotations. Like, can you imagine what you would deal with if I said, what was the height of point P 5 hours later? Well, now we have to do how many? It's not worth it. So, do we have a more efficient way? We do. One of the things we can do is we can eliminate the idea of full rotations at the very beginning. What I'd like you to do is just look up to your graph, the sketch that we were working on again, and notice that you have all the work you need there. Notice this. When I ask you at 40 seconds, I don't have to extend my graph all the way out to 40 seconds on my t-axis. Instead, what I can do is I can keep working on the cycle I can see. So, this action just took up 12 seconds for my period. Well, then to come back to the beginning again and use up another 12 seconds gets me to 24 seconds. Come back to the beginning again, take up another 12 seconds. That gets me up to 36 seconds. Now, what this question's really asking, since 3 full rotations gets me up to 36 seconds, for me to get to 40, I just need to go 4 seconds into the next rotation. So we just don't know where 4 seconds is yet unless we focus in on estimating. So one of the things that we can deal with then is to be able to go through and say, well, I'm going to take my 40 total seconds and I'm going to divide it by my period. That's going to go in 3 full times and 4 left over. You'll notice I didn't reduce my 4/12 because I don't really want to reduce that 4/12. Instead, that 4 is telling me to go 4 seconds into the next cycle. So, for me to be able to solve that problem, it would be the exact same thing as me subbing t equals 4. That is so much nicer, because now when I calculate it, I have my pi by 6 times 4, that's a 4 pi by 6, or I can reduce that to my 2 pi by 3. And now when I deal with my rotation angle, I can go directly there, and I've eliminated the need for multiple rotations. Okay, the next part. Let's talk about how we're going to estimate it. That I would hope as well, since we can see that that full rotation takes 12 seconds, and we know that our trig curves can be broken up into quarters, that we would then know that half of our rotation would take 6 seconds, and every quarter of our rotation would take 3 seconds. So I can break up my grid, and I know, at least at those quarters, where point P would need to be. And so if part C is really asking me, what is the height 4 seconds into a rotation, I know that I have to be in that purple highlighted section on my curve. So my estimation, I got to be a little bit below 6 meters. That's what I'm expecting to see. So let's go ahead and let's calculate it. Well, if I have my pi by, and I don't know why I wrote pi by 6, my pi by 3, then I have a, yikes, I have a root 3, -1, and 2 special triangle. So my cos for that is going to be adjacent over hypotenuse. That's going to get me a negative, and there is my 5 meters, and that matches with what my estimate would have been at that time. Nice. Hopefully some of that trig application is coming back to you a little bit from grade 11, but now we can also see the adjustment with radians, and we can be really efficient with what we do. Okay, let's pick up the pace on the next part of this problem. So part C says, at what time is P exactly 7 meters above the ground? We should be good then to sub an H value of 7 into our equation. That's going to get us 7 equals 2 cos pi by 6t plus 6, and we should be good to begin to solve. So we notice where our variable is. It's inside our ratio, so we have our trig equation. That means that I want to isolate it, so let's get rid of that plus 6 at the end by subtracting 6. We can then divide out the 2, and we come in on that point. Now, we get to that point, and you now have a cos equals 1/2. Let's keep in mind that, yes, the inside of that cos is really ugly right now, but who cares? Pi by 6t is really just like a variable. It's like a theta. And so the equation actually could be just like this. So let's not get distracted by the fact that we have something a little bit uglier inside of our ratio. That instead we say, okay, my cos is positive, and therefore I know that I could be to the right. And now that I see that my cos is 1/2, I actually know that this is a special triangle with related acute angles of pi by 3. So what I have then, what is inside my trig ratio could put me at pi by 3 in the first quadrant, or what I have inside my ratio could put me at 5 pi by 3 into the fourth quadrant. So we come up with those values and we should be good. Now, I want to make sure that we don't make some common mistakes. We're not done the problem yet, so don't get worried there. But I want to go back to something because there's a real common mistake that we might have come up with, and it can be a very costly one. I want you to take a look up in the top right corner when we created our equation, that there can be a very common mistake that gets made where you have a vertical shift of 4 on the end. Okay? I hope you look at it and go, why would anybody ever put a 4 when they try to build that equation? But because they saw that the bottom of the graph was at 4, they may have thought plus 4 at the end. When you're asked to build the equation of a function, it's not that costly of a mistake. However, when you're asked to do something with that equation, it can be. I want you to see what happens if I go through and I have a plus 4 on the end. Well, now when I go through to solve this equation, I would then subtract 4. I would divide out a 2. And now I'd have to go through and try to figure out what that pi by 6t is equal to. So at the very least, I would hope that you would look at that right now and say no solution. Because you notice that your adjacent side cannot be greater than your hypotenuse. Or at the very least, you said, I know that my coses can't be outside of 1s. So 3/2 or 1.5 is way too big for cos. No solution. So you then end up algebraically trying to tell me no solution. But meanwhile, you look back at the problem and you say, of course it is. The maximum height was 8. The minimum height was 4. Clearly there's going to be a time when it's 7 meters above the ground. So notice, when we build the equation, putting a 4 on the end isn't that big of a mistake. But when we go to use the equation, it can be. So let's leave that then as our 1s and we're good. Okay, let's jump back down now and let's finish off the problem. So we take a look at that, and now all we have to do is get the t all by itself. And so I would have some people that would kind of put the blinders on a little bit, and they would say to get rid of a times by pi by 6, I have to divide by pi by 6. And then that means since I'm dividing fractions, I'm going to flip and multiply. And then my pi's divide out, and I can simplify to 2. I would hope, though, that we could just kind of reduce as we go. And what I mean by that is, let's take a look at the second equation. For you to get that t all by itself, you notice your pi's divide out right off the bat. And so to then calculate it, really what we're looking at is 5 times 6 over 3. And I don't really care how you get to that. Maybe we cross-reduce, maybe we don't, but we should be good to come in on 10. Okay, now we may end up going, okay, so now I have to put my units on. Time is being measured in seconds, so I put on 2 and 10 seconds and we're good. And we got to stop for a second because that's actually not the answer to the question. That would be the answer to the question if our stipulation was the first rotation. But there is no restriction in the question. The question just says, when do you get to a height of 7 meters? So if you notice, this is an application question that comes back to general statements. Now, before anybody goes, oh, yeah, that's right, that's general statement. So it'd be like 2 plus 2k pi, and then 10 plus 2k pi. Because I know general statements mean I add on a 2k pi. Stop. 2k pi has no relevance in this problem whatsoever. That really, remember, that 2k pi was really full rotations. Any number of them. That's why the k was there. In either direction. So, how long does it take to do a full rotation on the windmill? Well, the problem told us it took 12 seconds. And so really what we get then is 2 seconds plus a full rotation. So 12 times k. K allowing us to have 2 rotations, 3 rotations, 4, any number of whole rotations. Or at 10, and any full rotation. There we go. If we're able to work our way through that, we are doing great. Great. Okay, we've got one more problem to work through, and I think we should be good. Notice that we're talking about a Ferris wheel problem. And so what I'd like everybody to do is just to tackle question 3A. So go ahead and give it a shot. Pause the video, read, create your solution. Okay, we should be back. So the first thing I might do is go ahead and put on a set of axes. It's a Ferris wheel question, so I know that that's going to put me in quadrant 1. I'm talking about height in the problem, and I'm talking about time. So we go through and we create our problem. So Ferris wheels, you hop on the ride at the bottom, and then you ride up, and then you ride down, and go. We need to have a graph that matches that. It would be kind of weird to hop onto a Ferris wheel where you hopped on at the top and then went down. I don't know if that would be a very funny ride. So we take a look at that green curve. If we were to label our key things, at the bottom of the ride, the passenger is 2 meters above the ground. The diameter of the wheel is 18. So if I go up another 18, then that's going to get me to my top. So that makes my top at 20 meters. And my period, well, this one gives me a little bit of work. So it tells me that I do 5 revolutions every 2 minutes. So what that could mean then is like 2/5 of a revolution per minute. But I feel like that might be a little ugly for us. That is, I just don't know if we want to introduce fractions for our period, if we can avoid it. So what one common thing would be is, since the problem doesn't define what units t has to be, why don't we pick what units we want? And most people would probably prefer to break things down into whole numbers. So when I see 2 minutes, if I change 2 minutes into 120 seconds, then I can divide that by that 5, and I'll see that I actually take 24 seconds to complete a rotation. I think a lot of people would prefer to use 24, that is, use seconds as your units as opposed to minutes. So I'm going to go through and I'm going to build my equation given that information. So first off, I would hope that we would all use a negative cos graph because my curve is starting at the bottom. Reflect your cos curve. Now that I have that, I can see that right now my height of my curve is 18. That's going to make my amplitude 9. If my period is 24 seconds, then I can use my best friend, that relationship, to multiply out my k, divide out my 24. That's going to get me a pi by 12 as my k value. Because I used a negative cos curve, that means I don't need a phase shift, so I have my t. Now I have to get to the middle of my graph. So the middle of my graph is going to be 9 up or 9 down from the top and the bottom. That's going to get me to 11. So I have a vertical shift of 11. There we go. Nice. If you came up with that purple equation, you are doing great. Okay, let's take a look at problem B. And I want us to be able to work our way through B. So let's do this in its bits, and I think it might be better for us to go through this together. What I'm going to do is I'm just going to write out that equation one more time, because I'm going to scroll this up so that we can really see the work we're going to do. So if I shrink that down a little bit and scroll up, that gets us enough room, I think. So the question asks, once the passenger reaches the top, how long does it take for her to get below 10 meters? Well, what I'm going to do is I'm going to solve for when does she get to 10 meters. To know at that point is going to be important. And then I can kind of adjust some things. So what I'm going to do is I'm going to sub in an h value of 10. That's going to get me that equation, and now I can work through to solve. I think we should be okay to get rid of the plus 11 on the end and divide out the negative 9 at the beginning. So let's get rid of the plus 11. So we're going to subtract 11. Then let's divide out that negative. We should come in on this equation. And now that we have our ratio isolated, now let's go ahead and solve for what that angle is. So my cos is positive. That's going to put me in quadrant 1 or quadrant 4. I take a look at my information and I recognize that 1/9 is not a special angle. So I'm going to go ahead and I'm going to use my calculator. I'll come up with an approximate. When I do my inverse cos of 1/9, I should get about 1.46 rads. And so if I was to come from that diagram up top, I then know that whatever's inside that ratio, pi by 12 t, has to give me 1.46 to put me in the first quadrant, or whatever's inside that ratio has to get me 2 pi minus 1.46 to put me in the fourth quadrant. Okay, I know that those equations are really ugly, but they're actually pretty easy to work with. For me to get that t all by itself in that first equation, I need to take that 1.46 and I need to multiply out the 12, and I need to get rid of the the times by pi. In the other equation, similar process. I need to get rid of a divide by 12, so I'm going to multiply everything by 12, and then I have to get rid of my divide by pi, or my multiply by pi, so I divide by pi. Okay, I come in on that scenario. Now I'm going to push some buttons. And so as I work my way through, this first one's going to get me approximately 5.58 seconds. And this last one's going to give me approximately 18.42 seconds. So let's make sure that we've got our keying sequence down on our calculator to be able to come up with those values. If we have that, what I want to do is I want to come back up to our sketch for a second. And I want to break it down into quarters again, because I think that's going to be helpful for us to see the solution to this problem. Because neither of these are the solution to our problem. So let's take a peek. If I went back up to my graph and I broke it up into its quarters, if the full period took 24 seconds, then each quarter has to take 6 seconds. So for me to go to the bottom and up to the middle is going to take 6 seconds. The middle to the top will take another 6 seconds. The top to the middle will take another 6 seconds, and then we get to the bottom. So when this question says, once the passenger reaches the top, that means that I've got to go to the top. Now the question says, how long does it take for her to get below 10? Really what I'm looking for then is this instance. I know 11 puts me down the middle, so I need to know, when do I get just a little bit past the middle? How long does it take to do that blue portion on my graph? Well, right now, you should be able to tell me, well, if 12 seconds is when I hit the top, and the point that I'm looking at is right here, that being 10 seconds, we solved for that in B, that this position is your 18.42. Notice that the 5.58 is actually inadmissible. Not in our solution, so don't think that we have to mark it inadmissible, but it's inadmissible for us to use it because it would represent the time when we were rising to 10. So we then might say, okay, well then therefore my answer has to be take the 18.42 and subtract off the 12. And so we come in at 6.42. If you gave me an answer of 6.42, you were doing great. It's not correct, but you are doing great. Because this is where we need to work in the word below. That when we got to that value of 18.42, that value would have actually looked something like this. And we come to a rounding situation again. That because I rounded down to 18.42, I just follow my normal rounding rules, that time of 6.42 seconds would actually leave me just a little bit above 10 meters. I haven't got to that height of 10 meters yet, and so I definitely haven't gone below it. That the way that we make this adjustment is to simply ensure that we're going to round accordingly. So if I rounded just a little bit more up, then I will get below 10 meters. Tack on your units, and you are good. So we get to that point, and we have done outstanding. And for us, that's the last big group of lessons for us to work through. So I'm hoping we're able to work our way through this one. I know it was a little bit longer, but that'll be it for us this year. So I'm hoping that the lessons went well this year. I'm hoping that everything was easy to follow with, or relatively easy. And for those of you guys who stuck with it throughout the year, I'm super proud of you. Super proud of you. Okay, job now, jump in and get some practice. We're almost done. Great work.